Oh shit, didn't realise flash on. Alright, quick little shifty. This is the old my old maths club work. That was when maths club originally started, I believe. Matt Long, Ben England, Rami Singh. I did a drawing of a dot and some dimensions. But anyway, right, base / number theory. So I actually did this on the 5th of March. Would that have been the 5th of March 2019? Hold on, let me just look back. Don't judge anything you see in the background. It's like the trash of my thoughts. So yeah, so this would have been something I did on the 5th of March last year. It was with Ben England, expanding base knowledge. He had a degree in computer games programming for CDS to be taught to others in future. Matrices, which I didn't actually understand, so I had to learn them. CDS notes, that's me. Travelling salesman, distance problem, colour theory. That was actually that was a friend of mine who mentioned that during the thing. That was Big Matt, Mass Matt. So X-Men equals X to the 0 equals 1 equals Y. Why does anything to the 0 equal 1? That is a why question. I didn't get around to it. But here we go. So here is base / number theory. Does this make sense? You see, so when you have a number, this is your units figure. And what you do is you take your unit number. This could be 1 to 9 in base 10. We're looking at base 10 here. And you're actually doing, you're doing 1 to 9 and you're timesing it by 10 to the 0. So we know this is 1. So 1 to 9 times 1 is 1 to 9. And now you have 10 to the 1 here. Now 10 to the 1 is 10. So here in your tens column, you can have 1, 2, 3, 4, 5, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So again, what we do here is we do 10 to the 1, which is 10, and we times that one by it. And that's literally how it goes. Now, it's very nice in decimal, and then you go here, 10 squared, 30, like, you know. And so you can tell any number times that. So what I tried to write here, and I might have fucked this up. So decimal, you can see that says base 10. Hex says B16, so that's base 16. Sexamal is base 6 I've written there, and I've tried to do base 3, base 4, base 3, base 2. I can't remember how correct I did it. But you can try to follow this through. So a decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Because you get the decimal. So you've got 10. Now, it's base 10. Now, you've got 1 to 9, but your 0 goes into that, which makes your 10. 0 to 9 actually counts up to 10. So you get into 10 there. So in decimal, because 9 is your maximum unit, you get to 10. And you carry on. Now, what they do in hexadecimal, though, is because it goes up to 16. So you get 8, 9, but instead of 10, they call it A. And then 11, B, C, D, E, F. Because it's base 16, you have to get to 16 before you get round to 10 again. Sexamal, I don't even remember this. So this is probably, this is one that counts to 6s. As soon as it gets to 6, it ticks over. So basically, your base is when you hit your base, you tick over into 10 if you're using standard representations. You get 1, 2, 3, 4, 5, 6, 10, 1, 2, 11, 12, 13, 14, 15, 20, 21, 22, 23, 24. Curious thing to note, right? When you have base 10, you never see the number 10. Sorry, that's my air quotes. 10 per se. You get to 9 and you tick over. See, when you got base 6, you get to 5 and you tick over into 10. When you got base 16, you get into what essentially 15 and then you tick into 10 when you hit the base number. And you can get base 4 here, 1, 2, 3, 4, 10, 11, 12, 13, 20, 21, 22, 23, 30, 31, 32, 33, 40. That is base 4, and that should take us up to an equal equivalence of 16 in base 10, 10 in base 16 for hex, 24 in base 6 sexamal, 40 in base 4, I don't know what that is, and I had a base 3 here, but I fucked up base 3 somehow. Oh yeah, because I wrote 3. You never actually get the number. Whatever your base is, you never get that number in there. So if you've got base 3, you never actually get to see the number 3 within your system. This is actually something that will refer back a little bit to Imran, what I said about completeness and the incompleteness theorem, and stuff to do with the incompleteness theorem, completeness of logic, of theories. I personally believe, this is my personal belief when I say about that and completeness, that's why I personally believe you can have a base 10 system and your system is in base 10, but your system never actually has a single digit unit that represents 10. See, that's a single digit unit there that represents 10. See, A. That's what you get in a hexadecimal system. But in a decimal system, you get to 10. So basically what I'm saying is, in a base system, as soon as you get to 2 digits, the first time you hit 2 digits, that is your base number. 2 digits is your base number, essentially. And you can see that again with base 16. You hit 16, that's 1 digit, even though it's an F. I say digit, that's one alphanumeric character. And then you hit 10, that's your thing. Over here, your base 6, you hit 10. Over here, your base 3, you hit 10. Over here, your base... Oh, no, that's your base 4, you hit 10. Base 3, you hit 10. And your base 2, you hit 10 there. So you can kind of see the 10s slowly. If I had another base... Yeah, if there's a base 5, you would have had a 10 there. There's a 10 there. If you had a base 7, you'd have a 10 like over there and stuff. So that's just basic base stuff. Allow the base when I say that. And if you want to see how binary goes, to just follow the numbers down. I tried to do this quite in line. Forgive this, by the way. This is some random shit. Obviously, it's like 3 o'clock in the morning. This is just something that I had in my pad. So you can see, if you follow them along, how your numbers change between different bases as they count. I tried to keep them in order. I fucked up the 3s here, so just fuck them off. But you can see, as I said, base 10. Base 16, base 6, I believe that was, decimal, yes, base 4, base 3 before I fucked it up, and base 2. I'm just going to quickly flip over the page, but basically that's what I was saying about bases, just with what I've got written down already. I can do this again another time. Oh, this was on the next page. So if you had a number normally that was like 32,469,824, what you're actually doing is 5 times 10 to the 0 plus 2 times 10 to the 1 plus 8 times 10 to the 2 plus 9 times 10 to the 3 plus 6 times 10 to the 4 plus 4 times 10 to the 5 plus 2 times 10 to the 6 plus 3 times 10 to the 7. Now essentially I'll just try to do that a little bit here as well. Yeah, 5, 20, 8, 9,000. I stopped at like the 3, the 2 and the 4, but you can see that. So 5 plus 20 plus 800 plus 90. So yeah, 5 plus 20 plus 2, 800, that would be exactly that value. If we stop there, that's all it is, really. Hold on. So yeah, pretend that value is, as I said, 1 times 10 to the 0 times 1 times 5. So that's the 1's column. Oh, I don't even need to say 1. 10 times 10 to the 0 is 1, so I'll times it by 5. 10 to the 1 times 2, which is 10 to the 1 is 10, times 2 is 20. 10 to the 2, which is 100, times 8, which is 800. 10 to the 3, which is 9. And then what do you get? You get 9,000 plus 800 plus 20 plus 5, you get 9,825. Very basic stuff. Very basic stuff. And this is something I said here with base 2. So here it is. So what happens with base 2, I've written that up there. So you get 2 to the 0 is 1. Everything to the 0 is always 1. I need to look into exactly why, which is on the last page. And you get 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is that. So now when you get into binary or any sort of, basically any number that's in another base, now what we're going to do is we're going to take 0, 1, 0, 0, 1. Now what I know here is I need to do 0 times whatever that is, 0 times whatever that is, and 0 times whatever that is. So those are all 0. But what I need to do is I need to do 1 times 0, 2 to the 0, which is 1. So 1 times 1, so I have 1 there. And I need to do 1 times 2 to the 3, which is 8. So 0, 1, 0, 0, 1 is going to be 1 times that, which is 1. 1 times that, which is 8. So it'll be 8 plus 1, which will be 9. Essentially, 2 to the 3 times 1, 2 to the 2 to the 2, plus that is equal to 9. That's binary. Here we've got another binary number. What have we got? 1, 2, Okay, so this would be 1 times 1 plus 1 times 2 plus 1 times 8 plus 1 times 16 plus 1 times 32. So that'd be 32 and 16 is 48 plus 8 is 56 plus ignore the 4 plus 2 is 58. This should be 59, I believe. 59 I've written down there. 32 is 2 to the 5. 59. Oh, this was a curious way you can do some stuff with bitwise numbers in binary. But yeah, ignore some of how this is going. This is some work I'd said. Count. Oh shit, I can't read that. Count to 2x and use subtracted difference for absence. I think that says count towards or count to. I don't know what that. I do not know what that word says. But yeah, there's a little bit more. And so you can see in binary, that number, 1111111, would be 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. That number, by the way, I know what that number is. Because if this was a 1 and all of those were zeros, this 1 would be 256. And so this number is actually 256 minus 1. This number is actually 255. Because this 1, imagine if you added 1 to this, it would go 1, 0, 0, 0, 0, 0, 0. So this is actually 255, and the next number along is 256. So if I put a 1 here and turned all of those to zeros, that would be 256. If I put a 1 here and kept all of those 1s, that would be 1 short of 512, so that would be 511. Anyway, yeah, binary... I don't know what this is, 2n to the 1, 2n minus 1, this is some... Oh yeah, 2n... No, this is something else, this is completely other stuff. Oh, quaternion multiplication, there you are, that's for you. Arif, you asked me about quaternions before. And John Cormac doing 3D space, I don't know what this is, that would have been about... modelling in 3D games and stuff. I think my base work is quite possibly done. Yeah, this goes into Pascal's triangle and into some other stuff. But yeah, that's basically base work for you. I'm sorry for the video again, not as comprehensive as it could be. 12-30 minutes, but that's basically base work and the bases, as I was saying. I just thought I'd throw it out to you because I already had it in my my little maths book. So yeah. There you are, and anybody else who's watching, I'll catch you guys later. Cheers, bye.